Okay, then next speaker before the break is Ulrich Berger from Swansea University, who will talk about non-strictly positive induction for breadth research. Please.
Hi, so thanks a lot for inviting me. It's really great to be here and to celebrate Martin's work. I know Martin mainly as a domain theorist. When I met him, he was a big guy in domain theory and then principal analysis, topology, functional programming. And I learned a lot from him. It would have been nice to write a paper with him, maybe still to come. But so I think he taught me a lot. He was also sometimes not so successful in teaching me, for example, ACTA. I tried, but there's more worth for me to look over the shoulder of others doing ACTA. Yeah, so thanks also for Paolo for giving the talk, which actually preempts a little bit the first slide about what I want to talk about. Yeah, it's maybe a bit rude to start the first slide with a code, but in this case, I think it's permissible because it's really beautiful code, and that's kind of the characteristic of Martin's work. It's always perfect, beautiful, and also curious, strange. I mean, always the magic comes out, and that's really characteristic. So here we see again the product of selection functions that Paolo mentioned, which is kind of a basis of a lot of work of them. And I also worked on that. But I think the beauty of this is that he really, Martin managed to kind of flesh out the essence of it. I mean, it's just a very simple, nice function. So you have given, so you have the type of selection function, x arrow r arrow x. So r is a result type, like booleans, and x is the set you're searching. And then we saw the product of two selection functions, but you may have a list of selection functions and product them all together. And that's what we see here, the big O times. We have a list of such selection functions for x, and now you want to have a selection function for lists of x. Okay. And the definition is very simple, it's just a three-liner. And as such, it's quite innocent because you have a list and you do recursion on lists. So you start with the empty list, so you have no selection function, you do something, and then you have a first selection function E and then the rest. And your recursive calls are always with a shorter list, so it's absolutely harmless. But the point is that interesting cases where this lists are infinite. So we're looking at Haskell types, which are not really types as in type theory, they are like domain theoretic types. So the elements of a list type, so the square bracket, contains everything. Partial lists, total lists, infinite lists of strings. And if you have an infinite list of selection functions, then this definition becomes problematic. Because what kind of recursion is that? First you think, okay, the result of that function is a list of x, and it's string. Could be a string, so this looks like a guarded recursion. You output the first element, and then you do something recursively. That's perfectly good. But if you look at what you put in the front, it's this x0. This x0 is again computed by a recursive call to that function, so that's not okay. And there is no way of putting this in any of the known recursion schemes to justify that. But the justification has to do, of course, with topology. This P, the little p, what is the type of P? Is the type, you have to replace here x by x squared, list of x. So it's a function from list of x to r. And if that is continuous, it will only use an initial segment of its infinite input. And here in the recursive call, you see, we stuff x in front. So we make an arbitrary choice for x. Then we put the x in front. So this P will only get lists that start with x. And if you repeat it, more and more elements will be fixed. And eventually P, because it's continuous, will not look what's belong. So you get x0, x1, x2, x3. And eventually it will be happy and return something. So the argument why this works is a continuity argument. Okay? But the continuity is, of course, not explicit in this definition. No, nothing says it's continuous. So it's a challenging magic definition. And the beauty is that if you start with a very simple case, so R and X just being the Booleans, where the selection function is trivial, so you look for have two Boolean values, you look for one is true if there is one. But if you did a product, you get a selection function for Cantor space. Okay, which is this matching thing. You have uncountably many spaces, uncountably many paths, and you find a path with a certain property. Okay. So this is taken here, this code is taken from a paper of Martin and Paolo, which is a very nice introduction paper. It's a tutorial about this topic. And there's an amazing variety of applications. Okay, so what I'm going to do in the talk is to show you a similar, not similar, but related function, which is also curious and is a little bit problematic, and it's interesting to find out why it works. Okay, I hope you find it interesting. Okay, as I said, with these selection functions, you can translate it into a continuation monad, and then you get quantifiers. So you can decide whether a predicate on Cantor space has a certain is satisfied if there exists an element. Okay. And now we choose another. I want to talk about another algorithm that's also patently non-self-explanatory. So this is a quote from Martin and Paul's paper. That's due to Martin Hoffmann, who is unfortunately no longer with us, and he uses also the continuation monad, but for breadth-first search. And also this algorithm is very curious, interesting, I find, and I'd like to give you a little bit of highlight of how you can solve the mystery, and also some questions of how you might formalize the reasoning about this algorithm. So that is posted on an email on the Types mailing list, and together with Anton Setzer and Ralph Mattes, we wrote a paper analyzing this algorithm and proving its correctness in different ways. So first, what is breadth first search? An example, here we have a tree, and breadth first means you go in layers. So first you take the top node, and then you take all nodes of level 2, 2 and 3, and then 4 and 5, and so you go level by level. That's breadth first search. So what you do, you compute the levels on niveau. So Ralph lives in France, so he use French word, niveau. You compute the levels and then you concatenate them all together. That's like the specification of breadth first search. Let's call this the specification algorithm. Okay? And here is this program in Haskell. So we have the data type of trees, binary trees with integer nodes at the leaves and also at the inner nodes. And the specification is just what I said. You compute the niveaus and concatenate them. And the niveaus are just computed, well, you do by recursion on trees. For a leaf, you just get to one level. And then if you have a node with two subtrees, you compute the niveaus of those. You zip them together and have the n in front. And the zip function is not exactly the same as predefined in Haskell, because what you do when you run out of one list runs out, you usually stop, but here we continue. So if one list is empty, we take the other one. We don't, so in Haskell, this would be empty. But otherwise, it's exactly the zip with concatenation function. Okay. So that's this very simple specification program for the breadth first search. And now let's look at Martin Hoffmann's very strange and fascinating program. So it uses, first of all, a fixed point of the continuation monad. So it's a data type of routines. And the routine can either be finished over, just a constant, or it is a function from routines to list of integers to list of integers. And we call this construct the next. Okay? So that's just an auxiliary data type. And then how does Martin Hoffmann's search work? In a similar way as the specification, you compute something else, like the niveau, but here you compute a certain routine, and this routine is computed by the function BR, and then the extract function turns this into a list. So the extract function goes from routines to integers, and the BR function interprets a tree as a routine transformer. And you use that transformer then with the starting value over. And the definition is harmless. It's by recursion on the tree. So for a leaf, you do something, and for a composite tree, you get these transformation functions for the subtrees, and you compose them with the K. Yeah, the K, the K must be a function from root to int, and you compose them, unfold C with it, the unfold function will come to a minute, and then you attach n in front. So that's very unproblematic. And the unfold is very simple. If you have a next function, you just remove the next. So next fk, unfold next fk is just f applied to k. And in the over case, you do something else because you can't do that. You say k applied to over. So you just check this is type correct. But it's not recursive, it's just the explicit definition. But the extract is strange. How do you extract a list from a routine? Well, for over, you do the empty list. But how do you extract from a next f? Well, you just apply f to the whole extract function. So this is type correct. It works, but it doesn't make sense. Strange. And what kind of recursion is that? You do the whole function and put it as an argument here. So this seems to be very, very strange. Doesn't make any sense at all. Martin Hofmann presented this as an algorithm in system F. And in system F, you can represent these fixed points of data types, of functors, of positive functors. And then actually it's interesting that the extract function becomes straightforward, but the unfold is the problematic one. Very strange. When you model this in system F, but I don't want to go into details there. But now let's just take it as it, not in system F, but just we assume, like as a domain theorist, well, you can take these fixed points, it's no problem, and we define a function. It's certainly a computable function, but it can be partial, because in domain theory, you have no guarantee that anything is defined. It could be undefined. Okay. So what's the verification strategy? Why is this function correct? And we do something, what I like to do is, and we want to extract the program, not just prove it correct, we just do some proofs and do program extraction via realizability, and then we get the program out, and we, by the sampling theorem, we know it's correct. Okay? And the correctness of our proof will only rely on the equations. We don't make any assertions about termination of these programs. And just have the equations are like axioms, otherwise it's like first order logic. Okay. So first we need to state what it means that the program is correct. So because we have these Haskell types which contain infinite and undefined things, we need to sort out, we need to separate the things we really want. So the labels should be really natural numbers, so they should be either 0 or the successor of a natural number. That's one way of saying it. The mu on top of the equal means it's the least set. It's like an inductive definition. 0 is a natural number, and if n is a natural number, then n plus 1 is a natural number. But it's equivalent to like this, a bit shorter. Okay? Because the least set predicate on the type int that satisfies this equation. Then the lists are finite lists of natural numbers. So a list is either empty or it's of the form n colon L prime, where the n is a natural number, and recursively the list L prime is a list. So it's again an inductive definition of the lists, completely straightforward. And the trees, we only want the ones that have defined labels. and a finite. So a list, a tree, is either a leaf with a defined label, or it's of the form node, and those subtrees are actually finite trees, and the label is also. So these are inductive definitions of the elements we really mean. And then the theorem says, whenever I define a tree, then this function here returns this function returns a finite list of defined elements, and it coincides with the specification function. So that is the correct statement. And here I just repeated that and unfolded the definitions of these two functions so we see it in front of us. So extract per T over equals concat with T. So that's the specification. And now how do we prove that formula? This is now just a formula that talks about these inductively defined predicates and uses the axioms of the equations of the programs as axioms. And just for a talk formalization, let's assume these are all base types, and we just have these functions as constants in our language. It's not so important. So it's like a first order set rendering of the whole thing. And now comes the interesting point. What do we prove about the extract function? So we define a relation, little rep, which is inductive, so the little mu. It's the least fixed point of a non-strictly positive operator. It uses this helper predicate is extractor. So if you look at is extractor, it has a parameter which is a relation, binary relation R. And this relation R occurs negatively. The is extractor depends negatively on R. And this is extractor here is used again negatively. Here. So it's twice negative, it's positive. So it's non-strictly positive. So there is a least fixed point, Tarski. And we can write down the least fixed point axiom, which just says it's the least fixed point. Okay, so this makes sense. I don't expect you to follow all the details, but you prove this theorem just by induction on that relation. It goes completely straightforward. It's just write down the proof, but it's a few lines. It's like almost trivial. Okay. So by induction on that relation, you can prove that this holds. So the extract is actually an extractor for that relation. And then the second part of the proof is about the BR function. And that says basically that if a list of list is represented by a routine C, then the BRT of C represents the niveaus of T. And you also have to add here this L as a, you zip the mid T with the L. Okay. So I don't know how to say a nice story about it. Yeah. It's in a way the BRT represents the SIBNIF function in its logical relation style. Okay. And this is a statement you can prove by induction on T. So T of T is inductively defined, and it's a bit of case analysis, but easy. And then you put things together, and you get this theorem. Okay. So the point I want you to remember is that we use a non-strictly positive inductive definition for lemma 1, and for lemma 2 we use induction on the tree. And then you can do program extraction. You can extract the types of the programs from the predicates, and then you see that you get the type of the definition of rep is just the routines, and the type of lemma 1 is root int, and the type of tree so 0 is this one. So it's just straightforward type extraction. So these are the types of the statements of these lemmas. Now, what are the programs? And the extracted program of lemma 1 is exactly the extract function. Lemma 2 is the PR function. The extracted program of the theorem then is the breadth first search of Martin. So in a way, it's a little circular program extraction because you start with the program and then extract it. But it gives you an assertion, you know what the paths mean. It gives you, I think, a nice insight in what this strange definition is about. And now there's one problem. If you do breadth first search, it's not important that the tree is finite. It's just important that it's finite branching. But you can do forever, you get an infinite stream of levels, no problem, and you concatenate them. So why? But the proof doesn't work for this case because it's an induction on trees. So something has to be done to get it for infinite trees. And you can do it, but then you change the strategy a little bit. You say, I define the trees predicate exactly as before, but instead of a mu, I write a nu. That means I take the largest fixed point, the co-inductive trees. The trees is, the predicate T says now simply it's a tree which is always defined. Yeah? Can stop or can go on forever, but you never have an undefined label. Okay? Then it has inducted the non-empty lists. And then you define a bisimulation between streams. Now we also allow infinite lists, and we say one or two streams bisimilar, and then define it in a bit unusual way. I say if two things are supposed to be bisimilar and they're not empty, so if you're in that case, then you must be able to write them in this way. They start with the same non-empty finite list, and then continue with something which is again bisimilar. So normally you say you have a first element, but it's more convenient to say you have a first initial segment which is not empty, which agree, where they agree. And then you can simply prove that this theorem holds instead of with equality, you have a bisimulation. Okay? And the proof needs a bit of generalization. I don't want to go into it. You have to generalize the statement slightly to make it work, so you prove something about forests instead of simple trees. Okay, that was, I don't want to go in more detail, and I don't expect you to read all these things in detail. You can have a look on the web page, I think the slides are. So the point was just to see that there's something interesting to be done. You have non-strictly positive induction, which actually is useful in practical things. And it's also a nice example of a co-induction to make it work for infinite trees. Okay, to conclude, so this example was done in, of course, implemented in Acta, but it was also done in Acta and in Haskell, but also in Acta and in Rock. But Anton and Ralph had to apply heavy sedatives to make these two systems accepted. So they didn't like it at all, so you have to switch up all kinds of things. And it would be nice not have to do this, to do it properly. So the question is, how do you do it properly? You have to formalize this. And possibly synthetic domain theory is the right way, because essentially the interpretation of the programs is naturally domain theoretic. Okay? And this monotone but not strictly positive induction can be computationally integrated. So it's possible. So one might consider it. And the final question is, unfortunately, the co-inductive proof gives you a program, but it's like the ordinary specification program. So I haven't figured out to find a proof whose proof works for infinite trees, but gives you actually the fancy Martin-Wolfman program. Okay, that's all, and thanks a lot, and thanks again, Martin. Happy birthday. Yeah.
That's right.
Yeah.
Thanks.
You called it extraction, but it seemed to me that you were doing the opposite. So you started with Martin's program and then you figured out which proof will compile to it.
It's a little circular.
It's not circular, it's the opposite procedure to me.
You say, okay, I only need these equations.
But for me, it's kind of impressive that you can, given a program that somebody else wrote, you can find a proof that. Anyway, very nice.
Yeah, just